Hi everyone, and welcome to Half Day Wednesday with Miss Besega. So, Wednesday on the half days, I want to make sure we slow down, rewind, and go over all the things you may have missed in the unit. I want you to see the big picture and how all these items fit together. So far in Unit 10, we started off with electromagnetic waves. Electromagnetic waves include everything from radio to micro to gamma rays, everything along this electromagnetic spectrum. You should know the electromagnetic spectrum in order from low frequency, low energy to high frequency, high energy, including the segments inside the visible light spectrum. Roy G. Biv. Now, electromagnetic waves all have a bunch of things in common. They travel at the speed of light in a vacuum, but they slow down when they go into other media. And that's because in other media, there's more particles in the way, causing the light to slow down. There are three equations we can use to calculate speed. We can calculate the speed using the definition of speed by determining the distance light travels in a certain amount of time. We can use the wave equation because light is a wave. And practically as we use these, if light is traveling through a vacuum, we could substitute c, or 3 times 10 to the 8th for v in either of these two equations. But if light is traveling through a different material, we need to know that material's index of refraction. The index of refraction is a unitless number between 1 and about 2.5. And think of it as how much slower does light travel through that medium than it does in a vacuum. So let's say light travels through water. I would take the speed of light in a vacuum and divide by about 1.33. So all our electromagnetic waves share all of those properties. But for the middle part of the unit, we're actually dealing with wave behaviors that are true for all waves. So refraction, reflection, diffraction, and interference actually can be done with any sort of wave. It's just easier to observe with light. So refraction is not just light. Refraction is when any wave enters a new material or a new medium. In changing material or medium, it changes speed. And as a result, it changes wavelength. And sometimes it changes direction. But during refraction, that doesn't change the color or frequency of the light. If we go to this handy-dandy simulation you have seen many, many times before, when light goes from one material to another, it refracts. And in the wave form, we can see that causes a change in speed. It slows down when it goes from air into water, but it also makes the waves closer together. These crests are closer, making the wavelength smaller. For refraction, back into ray view, we see that light forms a larger angle, a fatter angle, in the material in which it travels faster. Fatter angle in the faster material. Slower material gives us a slimmer angle. So what we could do here instead is we could also use Snell's law to figure out how the different indices and different angles can be used to solve for one another. If we knew the angle in both materials and one of the indices, we could find the missing index of refraction by calculating. But a funny thing happens here. If we go from a dense material to a less dense, a high index to a low index, sometimes Snell's law doesn't work at all. And that's because after a certain angle, the light can get trapped by refraction in a process called total internal reflection. You've totally seen this before. This is when light goes from a dense material like water into a less dense, lower index of refraction material like air. When that happens, light ceases to refract, or at least not by going into the new material like it normally does. For large angles, angles larger than the critical, you cannot use Snell's law because it doesn't change medium from water into air in this case. It stays trapped in the water. Essentially, at 0 degrees, there's zero refraction, or at least away from its initial path. And by increasing this angle, I see that the faster material has the fatter angle, but it's going to reach 90 degrees before my incoming incident laser does. And at some point, right around 40 degrees here, it reaches what's called the critical angle. At the critical angle, the light ceases to stay in the refracted material. Think of it as it bends so far away from the normal line that it gets trapped in the incident material. Everything bigger than 40 degrees, the critical angle, everything bigger than that angle, displays total internal reflection. Everything less than that angle displays both regular reflection and refraction. Notice that regular reflection obeys the law of reflection, so 45 degrees in, 45 degrees out. So the reflected angle is always symmetrical across the normal line. But for the refracted angle, we would have to go use Snell's law. Another thing we can use here is refraction also leads to an effect called dispersion. And dispersion is when light goes through a refractive medium, like a prism. And because of the prism's refraction, each color of light takes a slightly different path. White light, which is made up of all the colors of the rainbow, gets divided into its separate components because the red light doesn't bend as far as blue does. The blue light bends more away from its original straight line path here. And so the blue separates out from red, and that's how rainbows are made. So refraction and reflection both occur for any wave. So technically you could make a fiber optic cable like down here. You could make a fiber optic cable out of, well, any wave. It's just more useful with light. Similarly, both diffraction and interference occur with all types of waves. It's just more obvious with light. Now, diffraction is the property of a wave when it hits a boundary and either bends around it or goes through a small opening. But this picture I drew here is actually diffraction twice. Once through this opening and once through the adjacent one. Now, those two diffraction waves here, they interfere with each other. And where crests line up with crests and troughs line up with troughs, you get a constructive interference band, which we call an antinodal line. I've drawn this with water waves here. As water waves travel through these two openings, that means a person sitting on the shore right here would experience high amplitude waves along this antinodal line where the constructive interference occurs. But right next to it, along the nodal line, halfway between the two constructive interference points, this person on the shore would experience no amplitude. The destructive interference along the nodal line means no amplitude. But we can see this more obviously with light. The famous experiment was called Young's double slit experiment, and that experiment proved that light has wave behaviors. So, in this experiment, y is the distance between the two bright spots formed by light. If you wanted to repeat this with other sorts of waves, for microwaves this would be hot spots, hot, cold, hot, cold, hot. For sound, if you walked by this, this would be loud, quiet, loud, quiet, loud. But with light, we see bright spots, and y is the distance between them. Wavelength is the wavelength of light, usually measured in the hundreds of nanometers. So this would be 650 nanometers because red, though I would have to tell you how many nanometers it is. You're just responsible for converting it into meters and using it accordingly. L is a large distance. This should be on the order of a meter or two. That's the distance between your source and the screen. And finally, D. D is the size of these two openings, like the distance from one hole to the other. Putting it all together, and we can approximate how far apart the lines are. Oh, and don't worry about this M here. M stands for order number. Since you're always going to be measuring the spacing between two lines, and they're equally spaced, you can assume for all your problems that M equals 1. Kind of nice. So zooming out, putting this into perspective then. This is a unit studying light. We talked about the different types of light in general and their properties. We talked about 4 different wave behaviors: refraction, reflection, diffraction, and interference. So we're going to close out the unit with an important question. If light does all these great things, where does light come from? So we'll be looking at absorption, emission, and photoelectric effect on Thursday, Friday, Monday, and Tuesday. On the next half day Wednesday, we'll review one more time and then test on Thursday, April 9th. Best of luck and email with questions.